So today we're going to be looking at the second half of chapter 4, which is still going to be over integration, but we're looking at a couple of different techniques now to allow us to integrate some things that we wouldn't have been able to integrate before. So up until now, we really only used our reverse of our power rule. And then also we looked at some simple trig functions and then some simple natural log functions. But anything that is more complex, up until now, we haven't been able to do. So if we had something that looked like the integral of 2x times x squared plus 1 squared dx. Notice that because we have stuff on the inside of this function, we wouldn't be able to do it. Now, up until now, we would have just multiplied this out and then multiplied 2x to use our power rule. But there will be some cases when we can't use multiplication. So if we had 2x times the square root of x squared plus 1 dx, we can't multiply out or simplify that square root. So we have to have some other technique that basically allows us to undo or integrate things that would have used the chain rule to get there. So in general, U substitution is going to allow us to integrate functions that used the chain rule by rewriting into a general power rule or other known integral. So basically we're going to substitute out that inside portion that would cause us problems. So let's look at an example. So here, this is the example that I just put up. Again, with our previous steps, techniques, we would have just had to multiply this out and then distribute the 2x. But we want to look at a different technique. So what we're going to do instead is this time we're going to substitute out this middle portion. Because really, if I just had, say, x squared, I know how to integrate x squared just using our power rule. Right now the problem is we have stuff on the inside that we don't know how to do. So what we're going to do, just kind of like the definition says, we are going to substitute using a u. You can use other variables as well. We just call it U substitution because that's the most common variable that we use. So I would have u equals, and the more you practice this, the better you're going to get at figuring out what you want to use as your u. But in general, you're going to want to use kind of whatever's on the inside of this outer function. So my outer function is a squared. The stuff on the inside is x squared plus 1. So that's what my u is going to be. So this right here is going to become u squared. The problem is that we still have a dx and a 2x, and so we can't integrate something that has two different types of variables. Well, notice that our dx represents us taking the integral with respect to x. We're wanting to take the integral with respect to u. So the way that we accomplish taking or getting rid of that dx is by figuring out what the derivative of my u is. Because if I take the derivative of u, this would just be 1 du. And if I take the derivative of x squared plus 1, I would get 2x. My derivative of 1 is 0. And then I took the derivative of x, so dx. So now notice that these two things are going to become our du. So then we want to rewrite our integral. So here I have now just u squared. My 2x and my dx have been replaced by my du. And now we have something that can use just our general power rule. So I'm going to add 1, so I get 3 for my exponent. Divide by the 3. And then we have plus c. Except our original function didn't have u's in it. It had x's in it. So we need to, for our last step, replace our u with what we originally substituted it for. So x squared plus 1, and then it's still to the third power. And I still have a plus c. Alright, so let's look at another example. So this time I have the integral of the square root of 7x plus 9 times, or dx. So again, we know how to take the integral of something that's just a square root. However, the problem now is that I have 7x plus 9 on the inside. So we would have to figure out some way to reduce that, which we can't, which is why we're going to have to use U substitution. So again, my outside function is my square root, which means that I want to allow my inside function, so 7x plus 9, to be my u. So again, I'm going to take the derivative to find my du. We get 7 dx. So this time, my square root is going to become the square root of u. My dx is going to be taken care of by my du. But notice that we have an extra 7 here. I don't have a 7 in my integral this time. So what we end up having to do is I do have a dx. So if I can solve for dx here, I can just replace my dx with whatever I have on the left side of my equation. So notice that if I divide by 7 or multiply by 1/7, I can solve for my dx. And so this time, this is what we're going to replace our integral with. So I would have the integral of the square root of u times, and this time instead of just replacing it with a du, I need to replace it with a 1/7 du. Our 1/7 is a constant, so I'm going to bring it to the outside of our integral, and I'm going to rewrite u as a power of 1/2, because now we can use our general power rule. So I'm going to add 1, which is the same as 2 over 2, so we end up with u to the 3/2 divided by 3/2, which ends up being 1/7 times 2/3 u to the 3/2 plus c. And again, we don't want to leave our u there. So here I get 2 over 21 times 7x plus 9 to the 3/2 plus c. And if we wanted to rewrite this a little bit nicer, 2 over 21, my 1/2 would become a square root of 7x plus 9 to the 3rd power plus c. So again, we're looking for kind of our inside layer or part that we can allow that to be u. And also the key there is that we want to allow it to be something that we can take the derivative of pretty easily. So let's look at some trig examples. So on my first one, we have the integral of cosine of 5x dx. So notice that I only have one trig function, and inside of that trig function, I have a 5x. So again, in this case, my outside function is going to be my cosine. My inside function or expression is going to be 5x. So for this one, we're going to allow u to be 5x, which means that du is going to be 5 dx. Again, we need to solve for dx. So we would get 1/5 du equals dx. So now, substituting in, I get the integral of cosine of u times 1/5 du. My 1/5 is a constant, so I can bring that out. And then we just have the integral of cosine of u du. Again, this time we can't use our power rule, but we do know the integral of cosine. So we would get 1/5 times our integral of cosine is going to be sine of u plus c. And then my last step, again, remember, is to substitute my 5x back in. So that would be my final answer. Now, notice that the difference on our next one is that we don't just have one trig function. We have two. And so this time we don't want to just let our 5x be our u, because if we did that, notice that I would still have sine of u times cosine of u. And so that's not going to be super helpful this time. So what we want to do instead is allow our u to be one of our trig functions. And it doesn't really matter which one. You'll end up with the same thing either way. Your u sub will just be a tad different. But I'm just going to use my sine. So then if I take the derivative, I get du equals, well, my derivative of sine is cosine of 5x. But notice that we would have to take the chain rule, and so times the derivative of the inside would be 5 dx. I don't have an extra 5, so I do need to divide by 5. So then I have cosine of 5x dx. And notice that I have a cosine of 5x dx. So now, if I do my u sub, my sine of 5x becomes my u. My cosine of 5x is going to get sucked up into my du, but then we do have to have a 1/5 there. Again, my 1/5 is a constant, so I have u du with a 1/5 on the outside. And again, this is just my general power rule, so we add 1, so we get u squared, divide by our new exponent, add our plus c. So then notice that we will have a 10 in our denominator. And then again, we need to substitute back in, so we would get sine squared of 5x plus c. let's look at one last example. This one is going to be involving e's. So again, we have a lot going on here, but notice that everything is just over 1 e to the x. So before we get started with our u sub, sometimes it's helpful to divide out or simplify out if we can. So in this case, notice that if I divide e to the 2x by e to the x, I would subtract, and so we just end up with e to the x. Then e to the x divided by e to the x is just 1, so we just end up with 2 here. And then I have a plus just 1 divided by e to the x dx. So rewriting, I have e to the negative x, all of this times dx. So really notice, I know how to take the integral of e to the x. I know how to take the integral of 2. The only thing that kind of has 2 parts or 2 layers is going to be that e to the negative x. So notice that my exponent is going to be the part that we want to allow to be our u. When I take the derivative, I would get negative dx. Well, I have a dx, but I don't have any negatives in there, so we would divide that out. And because I'm only having to do the u sub with this last one, we are going to rewrite this as 2 separate integrals, because I can take this first integral with respect to dx. The second part here is what's going to cause me issues. So we're going to go for e to the u times negative du. So my first integral, so the integral of e to the x, or the antiderivative of e to the x, is just e to the x plus 2x. Again, my integral of e to the u is just going to be e to the u, but it is going to be times a negative 1. So I'm just going to change that to subtraction here in a second. And then our last step is to substitute that back in. So I have negative, so I changed to subtraction, e to the negative x, and then we need to add in our plus c. So again, remember, the biggest part here is that we want to try and first simplify if we can, which in this case we could, and then we want to try and figure out what we need our u to be. Again, a couple of key things. I'm looking for an inner layer and an outer layer, and we're also looking to try and switch it to something that we do know how to take the integral of. We know how to take the integral of e to the u, so it makes sense that we might want to substitute just this exponent.